ACE 111, Lecture 4 and 5, Set 3, examples in different abstraction levels. So far, we've seen various abstraction levels that are possibility to write in system Verilog. For example, the data flow level, behavioral level, switch level, and gate level. Now let's see some few examples of how this actually compares in practice. Here we were talking about a behavioral level, and in behavioral level, if you remember from what we've described, we just define the behavior in a defined way, but we don't really need to think about synthesizability into hardware. This is a higher level algorithmic abstraction. The constructs that we use for behavioral level modeling are the initial and always, and how we use it, we typically use it for sequential design. For example, in this case, we are using the case statement, and the case has the select signal. Whenever one of these is just activated, we are going to get the functionality and use the case with AND case and of course the AND module to describe the given behavior. The behavior model does not need to necessarily know in advance the number of clock cycles. This is a higher level behavioral model, and once we synthesize it, this is kind of how it looks like in this particular case. Now, if we think about a decoder, we could also think about this as a data flow model, which means that we are going to define how the data really flows in and out this. For that, we could use a truth table, and we define this in terms of a Boolean logic. A Boolean logic is a very common way how this data flow is typically described. And once we have a Boolean logic, what we could do, we could design the logic circuit, in particular in this case, and then just write line by line how these look like, how the logic expression look like in a module at the data flow model. Here, as you see, the data flow model uses a assign statements. You could also use always statement, but the always has to be in the combinational format. Now, if you synthesize it, we get this data flow in terms of the Boolean logic description that is synthesized into hardware. Now, if we want to think about the gate level model, we could just write the truth table and the gate level, but this time, instead of just writing that Boolean behavior like what we described last time, we are going to take each and every of these gates here. In this particular example, we have 6 gates, and then we are going to use the constructs that are in system Verilog available that define the standard gates. So we are going to use those with the name of the gates and then the input-output ports to describe this same level, same function in a different level, which is in this particular case gate level. If you look in this example that we just saw, you may think that the gate level model is similar to the behavioral model we've just seen before. For a simple circuit like that, this may be true, but in general, for general circuits, this is not exactly the case. The waveforms typically can generate different results because these are different levels of abstraction. But in this particular case, because the model simulation is kind of showing the simple signals that are running, then we could see the same timing behavior for all of this before. Let's go through another example, a full adder. A full adder has 3 inputs, A, B, and C in, and 2 outputs, sum and C out. And typically how we represent it, as we've seen earlier, on the left-hand side, we put the inputs. On the right-hand side, we put the outputs. And now, if we just translate it in a behavioral model, what we're going to do is we're going to just put the behavioral description of a full adder here, and we're done at the behavioral level. This is going to be translated into behavioral level of adders, as you see on this slide. Now let's take the same full adder and think about the data flow model. We just translate this behavioral level into the behavioral to the data flow model using the logic expression that describes the sum and cout as we know for a full adder. Now, if we do that, then we could write this in terms of assignment to P and Q, which is basically the propagation and the AND of the A and B, and then we write the adder in terms of the data flow model that way. And once we do that, we get this gate level description that is synthesized after we define the data flow model. Remember here, the data flow model is describing a sign, which is a combinational logic for the purposes that we have here. Now let's take the same full adder example and the truth table we've already seen and think about this truth table in terms of the gate level. We can just go ahead and write the gate level description of the sum and cout with respect to AND and OR and XOR gates, and then we could just easily go and translate it in this particular case into a system Verilog code. We define the wires that are connecting the gates, and also we're going to define the AND and OR and XORs like we've seen here, and write this module simply just by translating. And once we synthesize it, we get kind of a similar behavior of what we've seen before. But again, this is because these circuits are so small for understanding purposes that it may not reflect a real-life gate level versus a behavioral model if you're talking about a much bigger design. The simulation results are the same in this case for behavioral data flow and gate level model simulation. You could define a notion of time if you're talking about the simulation, and think about that to show the results in a timely manner. In the next set, we will be talking about the data types that are available in System Verilog.